But now, instead of talking about rotational kinematics and energy, we got to backtrack a little bit. We're going to talk about dynamics again. So just building on the same theme, we keep doing the things we've already done. All right, so we did translational kinematics, we did rotational kinematics. We did translational energy, we did rotational energy. All right, now we need to do forces, rotational forces. All right, so Newton's laws still hold. All right, they still apply to rotations, moving things. The same laws that we've learned before are the same laws we're going to use now. So Newton's first law says an object at rest will stay at rest. And an object in rotational motion will stay in rotational motion. With the caveat being, if there are no net external what?
Forces.
Whoa, 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 whoa. Uh-oh. Give me my brush, please. What did I hit? Abort. Control D. B, V. It's on the brush. Brush. Huh. I must have hit something very, very strange. There we go. And I lost my color. All right, we're going to do it. There we go. All right, no net external torques, not forces. All right, so that's the new wrinkle. So we can write down Newton's second law then, which doesn't say F equals ma, which says tau is equal to I alpha.
What is that?
Tau. That's a pretty good tau.
Is that a vector sign?
That is a vector sign. Equals I alpha. Vector. Yes. All right, this is a tau, Greek letter tau. Is the Greek letter that we use for torque. All right, you've already met I, which is the moment of inertia, the rotational inertia, and you've already met alpha. So what we're going to do today is talk a little bit about torque. Torque is the rotational analog to force, as you might have guessed. And it depends on a few things. So torque, the first thing that torque depends on is the force that's creating the torque. All right, so it's a rotational analog. Torque is dependent on a force. It's also dependent on the direction of the force. And it's also dependent on the location of the force. Go away, Doc. So it decides to be in the, it wants to be around. Oh, hi, Doc. Go away. Why are you there? Sorry, bear with me for just 1 second, because that's going to annoy me to no end. Doc. Size, position, scale, effect. Minimize. Not Genie, that takes extra. Automatically hide and show the doc. Go away!
Let's go to the apple top left.
Oh, I know, it should, there it goes. It was refusing to acquiesce. All right, So the torque depends on a few things. It depends on all these things. So I'm going to write down our basic definition of torque. Tau is equal to R times F times sine of theta, which sort of looks familiar. You've seen an equation that kind of looks similar with two numbers and then an angle, right? What was that again? Work. All right, so sort of, similar, think of it sort of like work, where angle matters and the magnitude of the two vectors matter. So these are really, R and F are both vectors. We care about the magnitudes in this case. And torque itself is, yes, a vector, but right, this is the magnitude of the vector torque. All right? So you know what force is. F is just some force. R is the distance between the force and, we're talking about rotations here, so the distance between the force and the axis of rotation. And theta is the angle between R and F. Okay, so that's how you calculate torque. Let's do one example before we quit for the day, just calculating a torque. All right, so the example is this. You apply a force of 30 newtons to a wrench in order to turn a bolt. The force is applied at 60 degrees to the wrench. And I want to know, what is the torque on the bolt? All right, so the picture looks like so. All right, here's your wrench. You're trying to loosen up this bolt. You apply a torque, and we're just gonna go with 0.1 meters. So the distance is 0.1 meters from the axis of rotation, and you apply a force. Oh, that's not right though, because you apply it at some angle. All right, so here's your force. And you applied it at an angle of 60 degrees to the wrench. Now, if you've done any work in a garage or on a car or anything, you probably already have experienced this. If you're trying to loosen a bolt that's really hard to get off, you don't apply it at some weird angle. You're probably pushing it straight perpendicular to the wrench, right? Because that makes it easier to get off. In addition to that, if you have a bolt that you can't get off, the first thing you do is you go get a bigger wrench. All right, if you can't get the thing off, you got to get a bigger wrench. Or you do what some people do, is you stick a big old tube on this thing and you make it a long tube, and it's the same exact thing. Okay? All right, all you're doing in that case is you're applying the same force, you're just maximizing the torque. All right, so if you've done this sort of thing before, that's what you're doing, is you're maximizing the torque. That's why pickle jars have really big openings. I mean, kind of big openings. If they had small openings, you'd never be able to get the stupid lid off, right? Because they're on there so tight. Big opening. What? They just make the pickles smaller.
You couldn't reach your hand in the jar. It's too small.
There'd be a special pickle removal utensil. All right, so let's calculate the torque here. So I already told you that torque, the magnitude of the torque, is equal to R times F times sine of theta. All right, well, I've given you R, it's equal to 0.1 meters. I've given you F, which is 300 newtons. I think that's what I said it was, 30 newtons. All right, and I've given you an angle, 60 degrees, sine of 60 degrees. So you could calculate that, and you get 2.6 Newton meters. No, we're meeting the unit for torque. Newton meters, does that sound familiar? Sounds like a joule. This is not a joule. All right? Whenever you're talking about torque, we never say joule. We say Newton meter. I know it's weird. They are the same, though. Okay, this is a Newton meter. Now, a torque is a vector. So what do you think the direction of this torque is?
Is it at another angle? Or there's a triangle angle?
Southeast? Well, I mean, fundamentally, what we're doing, we're rotating something, right? So the force is applied this way, we're going to cause a rotation this way. So one way we could say that is counterclockwise. All right, that's fine. Other people, and we probably won't get into too much detail here, this counterclockwise rotation, all right, is equivalent to saying in the z direction, in the positive z direction. Which, in this case, if I said that x and y were this way, then z would be out of the board. Okay? So coming out of the board. So we associate positive, so note this is positive, we associate positive with counterclockwise. So if you ever have a counterclockwise rotation, that's in the positive direction. If you have a counterclockwise torque, that's a positive torque. Next, when we come back tomorrow and start to talk about adding up torques, you have to assign a direction. Counterclockwise is positive, clockwise is negative. Sean, you look confused. No, thought you were going to ask something. Okay, so we'll come back tomorrow, do some more torque examples, and then we'll move on to equilibrium. Don't forget about your quiz.